Hello and welcome. I hope you are having a great day. In this video, we are going to understand an important boosting algorithm called adapt adaptive boosting or AdaBoost. Okay, let's see what it does. So what is adaptive boosting? So what adaptive boosting does is that increases the weights. So there in boosting, what we understood, right? There will be series of models, very weak, high bias models. So there will be learner one first model, second model, third model. So first model will make some, say for example, if you are doing classifications, so it will make some um, predictions for all those classifications, and what so it will get some of them as right model, second model, third model, like this in boosting. So some of the predictions will be right, some will be wrong. Okay, for this, some will be wrong. There will be more rights, say. So what it does is, in the next model, when it feeds the next model, so this is your these are your data points. Okay, these are, say, data points. We have 5 data points. So it made correct prediction on 3 and wrong predictions on 2. So what it does is, for the next model, when the next model is trained, the weights of these misclassified points will be increased, so that the model focuses more on the wrong predictions. That's the whole idea. The weightage of mistakes is increased for the subsequent model, so that the next model focuses more on what was the mistake, and whatever is right, everything's working fine, no problem, let it go. You have learned that. Okay, that's the basic idea of adaptive boosting. That's what is the adaptation about. You increase the weight. Okay, what it says, you increase the weight of misclassified data points after each iteration. Each iteration we create a different tree, and the trees are created sequentially. That's the idea of boosting, right? Forcing the next week learner to pay more attention to the difficult cases, that it was difficult, that's why the earlier model made a mistake, right? And this is commonly used for classifications. Adaptive boosting. Okay, let's see a simple analogy to understand. Say for example, there is a teacher who is teaching students. So he gave him a practice test, first test. Okay, he got some right and some wrong. Then the teacher found out that he's struggling on hard questions, so the weight for the hard question is increased in the next test. So this is a second test. Say for example, geometry concept, these are hard for him, so weight of all those problems that he made mistake, all those concepts will be increased. And now the next one, next exam, he will focus only on the hard question and try to get it right. And subsequently, whatever he makes, say for example, in next exam he makes mistakes on algebra, so in the next exam he will be focusing on algebra more. Now geometry is done. That's how you learn sequentially. And finally, you see the big circle. So whatever mistakes are there, the weights on that is increased. And then finally, so the tests on which he performed well, those are the strong models. Okay, and those will get a higher weightage, means he is doing well. And wherever he is not performing well, those tests will be given low weightage. That's the broad idea. Okay, and then we combine all those. So all those tests where he performed well and then where he didn't perform well, and there will be weights assigned to each one of them. And then finally we'll combine all the test results, 1 2 3, all the test results, and get a final verdict, that what is his final prediction, what is his final score, basically based on all the tests. So the idea is, wherever he's making mistakes, the next test, those type of questions, those questions weightage will be increased, so that the model focuses and learns those concepts also. The kid focuses and learns those concepts which he didn't focus in the which he didn't get right in the first test, so that he gets knowledge of, or the understanding of all the concepts, and he becomes a better student, right? Okay, that's what how our models learn. So in this, I told you, right, we do very basic or high bias models. So those are called decision stumps. So these are weak learners that are typically, okay, depth of only one split, 2 leaves. Okay, let me show you. So for example, this is, so you have one condition, one root node, income is greater than 1000k, and there are only 2 options, yes or no, credit worthy or not credit worthy. So this is your decision stump. It looks like a cricket stump. Okay, there are 3 wickets. It looks like a cricket stump. Okay, that's why it is called a stump, 3 wickets. This is an example. So let's see that adaptive boosting algorithm. This is the AdaBoost algorithm. So this will be covered in 2. So what do? We initially start with, say for example, there are n data points. Okay, we start with n data points and we assign weight of 1 by 1, 1 by n equal to for the equal weights for all the data points. That's to start with. So initially everybody has equal weights. Then we build a decision stump that minimizes the weighted classification error. So we build a decision stump which will make most classifications it will get right, and then we'll calculate the error. So the error will be sum of all the weights. Okay, so whatever is the weight, it will be sum of all the weights will be my error. So the total you have 1, right? 1 by n. So you will be adding 1 by n, 1 by n times. So finally this error will be 1. That's the maximum value it can hold. And whichever classification it has got right, that will be 1 1. Okay, so it will be 1 by n. So say for example there are 10 data points, so each one will have 0.1 0.1 right. Say for example it got 8 right, 2 wrong, so it has got 0.8 right, 0.2. So the error here will be, okay, the error, the net weight, whatever total error is, summation of weights, whatever weight it has got. So the net error is 0.2 only, very less. Okay, so whichever it has got wrong here, so those will be counted as summation of weights finally. Okay, and how do we get the weights, we'll see next also. Okay, so those are the, now you calculate the error rate till step 3. Let's see step 4. Now we determine the amount of say, that is the weight of each stump in final decision. So there will be multiple stumps. This is stump 1, stump 2, like that. There will be different decisions like that. Okay, that will be number of iterations we want to train. More iterations, more number of stumps will be created. Okay, and the bias will be reduced even further. So there's one concept called amount of say, how much each stump will have a say in the final boosting ensemble. Okay, the collection, the combination. So this is given by a term called alpha m. This is alpha m. This is a formula. 1 minus em was the error that we got, that was summation of weight, and by em. So this is half log ln, that is log of e, natural log, base e. So the error is low, that it results with a very high positive alpha, high influence. Means if it is making very less error, means that tree is good and it will have very high say. For example, if it is making a 0.1 error, okay, 1 is the max. Okay, so 1 minus 0.1 by 0.1, so this should be like 0.9 by 0.1, that is natural log of 9. Okay, that is will be a big positive number. So alpha m will be that value. But if it is making, okay, half of randomly 50% of them right, so it will be 1 minus half by half, so that will be equal to 1 half by half. So log of 1 is anything is 0, means it is making random guesses, 50-50 right, 50 wrong. So alpha will become 0 and it will have no influence. So the value will be from 0 to that can go till infinity, because log this can go till infinity. The error becomes 0. Ideally if error becomes 0, this will be 1 minus 0 by 0, that will become infinity, and log of infinity will be infinity. So this term can go up to infinity, but ideally there will be some error because these are very high bias. So but if it is making 50% right, then the influence is 0, and there can be negative also if it is making even worse than that. But that is not what we are looking for. So anything 0 or above, sorry. Okay, so this was the page. Yeah, it's doing random guessing. Then that is your say. Better, less error means you are a better model and you have a higher say. As simple as that. If you are making random guesses, 0 say. 50-50 means 0 say. And then update the sample weights. We told, right? Misclassified samples, the weights will be increased by how much? By e to the power alpha m. You see, this is natural log here, so automatically this e to the power alpha m, if we get the log out, it will come from there. So all these weights will be for whichever the classification was not correct, their weight will be increased by this factor e to the power alpha m, and then correctly classified, the weights will be decreased by e to the power minus alpha m, that is 1 by e to the power alpha m. Their weights will be reduced because you have got them right, so no need to revisit them, reduce their weight. And then finally we normalize it, that all new weights are what you will get new weights after increasing and decreasing the weights for correctly and misclassified, and then you sum them up all together and you divide by the total weight, so that again the total weights be equal to 1. Okay, So that's the way this algorithm functions. And then iterate for specified number of estimators. That is how many estimators you want. More the estimators, more the bias will be reduced. Okay, this is an adaptive boosting algorithm in nutshell. Let's see how we make the predictions. Okay, once we have the model ready, now we want to test it. How is it functioning on a new data point? Okay, to classify a new data point, every stump makes predictions. So if you are doing a classification, so every stump will make a +1 or -1 classification example if you are doing, and then these are multiplied with the respective amount of say that we calculated, alpha m, and then all of them are summed up. So all the trees will have their corresponding alpha m value, what is my say, and each tree's prediction will be there, whether it will be 1 or 0, 1 or -1, sorry, if it is 1 -1 classification, two labels, so each tree's prediction, and we'll multiply them and sum up all of them together, and finally the total weighted sum. Weighted means that is coming from this alpha m amount of say. If it is positive, then the final label for this point will be positive, else negative. Simple. These are adaptive boosting algorithm. Okay, but there's one catch. It is sensitive to outliers, because if outliers, they will not be classified correctly. They'll be, because they are outliers, so it will keep on boosting its weight so that somehow it's classified, and that's why it will be like, it will aggressively increase the weights for misclassified points. It may over focus on noisy outliers, hurting the performance. So just to fit that, it can just keep on increasing the weight so that it is able to get it right. Okay, and that's how it is prone to fitting to outliers. So more number of iterations you do, more it will keep on increasing the weight by e to the power alpha m and try to fit into that. So that hyperparameter tuning we have to do. Okay, let's see in the infographic. Say for example, if you're doing fraud detection, so we are creating multiple simple decision stumps. So these are decision stumps. So for example, first round, in the first tree 1, okay, we check whether it's a foreign transaction or not, yes or no, and then if it's yes, then how many are fraud and how many are not fraud, yes and no. Okay, so yes and no is for how many is fraud and how many is not fraud. So out of them, in foreign transaction also, some of them can be not fraud, so there can be some legitimate transactions here. Okay, but whichever is fraud transaction here, these in the next iteration, in the next tree, those weights will be increased by the amount of say e to the power alpha m, and those weights will be increased. And now the next iteration, we can check some other condition. There will be another decision stump, whether the amount was greater than 5,000. Similarly, it will get some right, some wrong. So whichever is wrong will increase the weight, and for the correct ones will decrease the weight. So all the data points remain constant. And then say for example, the transaction was late night. Say it as after 3 a.m. or something. Then whether it's fraud or not fraud again, and if it's fraud, and how many of how many of the transactions it got right and how many of it got wrong, the weights will be updated accordingly. And finally, we have a voting. So we have 3 trees, 3 stumps. It can be shallow decision tree, it may not be specifically stump. It can be a shallow decision tree also, not more than like say 8 depth or 10 depth max. Okay, and each one will have their own say, and then we sum them up all, and finally whatever is the verdict, whether it's fraud or normal transaction, not fraud, we get the verdict out of it. So this is a representation of that. So it is not exact, but these are all AI generated images, so there will be some mistakes in all the images that I'll be using, so keep that in mind. Okay then, so that's all for adaptive boosting. I hope that was helpful, and then in next video we'll start gradient boosting machines, very important, and then we will, in that series, we will understand XGBoost, etc. We'll also understand what is the gradient boosting machine algorithm first, and then we'll upgrade to XGBoost, the advanced topics like GBM and CAD boost. Okay, so that's all for this video. Thanks for watching this video. Have a great day ahead, and bye for now.